Hello, this is Reza. I'm very excited about joining this very interesting event. I'd like to thank the organizers for this invitation and also for the amazing program. I'm going to talk about trustworthy machine learning from the lens of data privacy. And I'm going to highlight the results of one line of research that we have been working on in the last couple of years, which are presented in these three papers. The works are led by amazing PhD students, Wangan Chang, Martin Strobel, and Liwei Song, and is a joint work with Yair Zik and Pratik Mittal. Machine learning is basically solving a bunch of optimization problems. And a wide range of these problems can be formulated as what is known as empirical risk minimization. I bring this up because I want to highlight the term risk here, which ironically refers to a very narrow notion of risk and reflects only the performance of the model with respect to its prediction errors. Ideally, we want to quantify this risk and minimize it for the whole data distribution, but because we cannot exactly know what the data distribution is, we quantify this empirically on a set of data known as the training set for the machine learning algorithm. So this risk minimization based on a very particular objective function, as well as this empirical evaluation of the risk on the training data would significantly influence the behavior of the model, which goes way beyond its prediction accuracy. So it causes many concerns, and it leads to some unintentional consequences which are covered in the broader area of trustworthy machine learning, which I'm going to very briefly go over in the next few slides, which are about the requirements that we have with respect to data protection, fairness and privacy, with respect to interpretability of the models, and also with respect to the robustness and security of machine learning. So, as we all know, machine learning models have got really complex. We don't really know what features are being extracted from data and what exact rules are being used for, say, data classification. And this is getting more and more complex. So there is this demand that if I'm going to use this machine learning algorithms for some critical decision-making processes, I need to know why the model comes up with a particular decision, and what are the decision rules and what important features in the data led to this decision. So there are a wide range of techniques. This is an ongoing research, and a number of interesting methods have been proposed for training a model which is more interpretable or to explain the model decisions. Another very important aspect of responsible computing and trustworthy machine learning is fairness, because these algorithms are shown to have very discriminatory behavior with respect to some subgroups in the population in all different types of data for different tasks. It makes it easier to see it through an example as to why a model would behave discriminatory. I want to go back to what I mentioned about optimization problems and the way that we solve empirical risk minimization, that the objective function and also evaluation of that on empirically on the training data would lead to this algorithmic bias. The algorithm is agnostic to, is unaware of the subgroups. The only thing that wants to do is to minimize the prediction error. So for example, in this binary classification task, you want to find the line that splits these two classes, which results in the minimum error. But if we look at different subgroups, then there might be one minority group which is distinguished based on the gender, race, and other so-called sensitive attributes, where the model has a huge error. Basically, the whole subgroup is completely ignored because they do not contribute significantly to the total error that the model minimizes through that empirical risk minimization. And it's not hard to see that by slightly changing the line, we might come up with a classification model that has more or less the same error on the majority group, but performs much better and equivalently on the minority. So the objective of algorithmic fairness is to understand, first of all, why the models might have some bias, and show it in the case of many different applications, but also to come up with a definition for bias and also the algorithms that implement that definition. With respect to data privacy, if you look at the pipeline of machine learning, from the process of training on the training set to the inference on some input queries, the whole process might leak information to different kind of entities. So for example, the entity that does the training or does the inference has direct access to potentially sensitive data and might lead to direct information leakage. What is something more subtle is the indirect leakage of information about training data through the model predictions and parameters. An adversary who is just like a curious user of a machine learning system might try to reconstruct information about the training data by just querying the model, or machine learning as a service platform that has access to the model parameters trained on some sensitive data might be curious as to what data point has been in the training set. There are a number of different attacks that could be classified basically roughly into two classes of attacks. One tries to reconstruct information about records in the data set. So for example, in NLP task, we want to reconstruct the sentences that were in the data set. And also the other one, which are known as membership inference attacks, try to tell if a particular data has been a part of the training set or not. So these different risks and information leakage could be prevented or mitigated through different types of techniques for example, secure multi-party computations can help us to mitigate the risk of direct leakage, and differentially private algorithms can help us to mitigate the risk of indirect information leakage. Last but not least, machine learning algorithms are shown to be very susceptible to a wide range of attacks, where the attacker might change the data during the training or slightly change the data that is the query for the machine learning algorithm during the inference time to influence the decision of the model. Here, I would highlight and focus mostly on the latter class of attacks, which are known as adversarial examples, or also evasion attacks, where the attacker modifies the input in order to influence the decision of the model. These are shown to be very hard to detect and also prevent, and there's a huge line of research on designing machine learning algorithms which are robust to these attacks. So voila, here we have all these different requirements. And as I mentioned, in each of these fields, there are separate techniques as to how to measure the risks and how to design machine learning algorithms which satisfy the criteria for interpretability, fairness, privacy, and robustness. The main question here is, if I want to go and build a system which is trustworthy and is robust, fair, privacy-preserving, and interpretable, number one, if this is possible, number two, what are the trade-offs? And there are so many different trade-offs that could be discussed, but for the purpose of this talk, I focus on the relation between all different aspects of trustworthy ML and privacy. So we are going to see fairness, interpretability, and security, and the mechanisms that satisfy them through the lens of privacy. We are asking whether trying to make the model interpretable or explain the model, try to making the model fair and trying to make the model robust would have any unintentional negative consequences with respect to data privacy. Are they going to make the model more vulnerable against inference attacks, or making it harder to satisfy privacy? So that is basically what I'm going to cover. I'm going to go over each of these, and before that, I'm going to actually define what we mean by privacy and what is the measure and the metric that we have for privacy. My focus will be on indirect information leakage about machine learning algorithms, where a curious adversary might want to reconstruct information about the training data and learn information about the training data by looking at the model predictions or parameters. You admit that by interacting with the machine learning model, essentially you are learning something about the training data. So we have to be very clear what is considered as privacy violating and what is considered as information leakage, as opposed to just learning general information. So we define leakage as basically the information that you learn about the training data because they were part of the training set, right? The information that you learn about the individual records in the training set, which goes beyond the information that you're learning about the underlying distribution. And that is somehow could be also better understood by defining a game, an indistinguishability game, where you have two cases, two models, which are trained on exactly the same data, except that one of them has a record which is not in the other data set, right? So we have two models trained on two so-called neighboring data sets. And the objective of the adversary is to tell them apart by getting predictions from the models or by looking at their parameters. One way to measure this, the success of the attack in this game, is to design membership inference attacks, where the adversary's objective is to tell whether a particular data point X has been part of the training set or not. And here in the case of indistinguishability games, we are asking whether that one single data record, which is in one model and is not in the other model, could be detected by the adversary. So the attacker can look at different kind of signals that he gets from the model, but you can imagine that in a very simple form, you can look at the you can query the model with the data point X and look at the uncertainty of the model or look at the loss of the model on that data point and see if it comes from the camp of or the distribution of the loss for the training data versus the distribution of the loss on the test data, expecting that the distribution of the loss on the test data is much larger in values compared to that of the training data. I'm not going to go over the algorithms for these attacks, but these attacks have been well recognized in not only in the field of privacy in machine learning and the follow-up technical developments on that, but also in many AI auditing frameworks and AI guidelines towards having trustworthy machine learning as a methodology for quantifying the privacy risk. And so, for example, if you want to implement data protection impact assessment in GDPR, evaluating the privacy risk of machine learning, these tools based on membership inference attacks could be used. So there's a tool that we have developed, an open source tool that can be applied to a wide range of machine learning algorithms for different tasks from vision to NLP that could be used by practitioners and all, as well as researchers to evaluate the privacy risk of their models and systems. So this is exactly what we are going to use as a measure for privacy risk when we are going to go over different trustworthy ML algorithms. So let's look at some insights that we get from this tool and the algorithms for a membership inference attack by attacking some pre-trained models. So we look at a couple of years ago at different model architectures for training a classification model on C400, for example, and other data sets. In particular, for example, the model with the best test accuracy and the best generalizability on test data. And we evaluated the performance of membership inference attacks to quantify the privacy risk for different type of models. Some of them leak a ton of information just through their predictions. But something that is very interesting and I want to highlight here is that the model that has the best performance on test data has more or less the lowest privacy in the white box setting where the adversary has access to its parameters. So this is something which is also highlighted in a recent paper by Vitaly Feldman, very, very interesting and influential paper on looking at the relation between generalizability in machine learning and also memorization for long tail data. Something that here we are showing empirically is that the larger the capacity of the model is, that enables the model to search for an optimal model parameters, would enable it to memorize a lot of information that contributes to the generalizability of the model, but at the same time, the same capacity, the same kind of patterns that are memorized would enable an adversary to infer sensitive information about the training data. So there is this trade-off between the accuracy of the model, even on test data, and privacy. So some other set of insights, the more overfitted the model is on part of the distribution, and the more it memorizes information about that, obviously leads to higher attack accuracy and more information leakage. Something which is also worth mentioning and highlighting here is that the privacy risk is, of course, not the same across all the data in the training set. And notably, the smaller groups would have higher privacy risk, as it is harder for them to blend into the general patterns that the model extracts from the typical large data. So these are usually at the tail of the distribution. The model needs to memorize them in order to be accurate on them, and that leads to information leakage. Okay, so now let's go through Trustworthy ML one by one, starting from model explanations. The question you're asking is if having access to model explanations would result in more information leakage about the training data compared to just getting the predictions in a black box setting. So here we study the feature-based post hoc model explanations. A very good example of this is when we measure the gradients of the model with respect to the input to find out what are the influential features. There are also other variants of this, for example, which are mostly based on local approximation of the model around the point of interest and so on and so forth. But here I'm just going to focus on these gradient-based methods for the results that I'm going to show. And let's do some analysis on synthetic data where we can control the complexity of the data, the complexity of the task. We increase the number of features, and also we increase the number of clusters in the data where we are doing the classification to produce the data that is used for training a classification model. And we look at just the norm of the explanation for a data point, which are basically the gradient of the model with respect to its input, on test data versus training data, on the data which was part of the training set, the members of the training set versus the non-members. And we show that as the model gets more complex, as the data becomes of higher dimension, it is much easier to distinguish between members and non-members. This is basically the case for most of the models for which we want to do model explanation. The tasks are very complex, data is of high dimension, and we expect that they would leak significant amount of information by just looking at the model explanations. So if you look at some real data and computer vision models that we have trained, and some other type of data, we could see that the leakage of the model about its training data, in the case where you're just providing the predicted label plus explanation, is more or less the same as the case where you have access to the logics of the model, the exact precise output layer of the model. Something which is more interesting than showing that there is leakage is that there's a disparity of leakage. The minority groups, the classes for which we have fewer data points, for example, when we have an unbalanced training set, the leakage is much more compared to the majority group. And if you think about this, the minority group is exactly the group for which we need the explanation, because the model might behave in a way which is not easy to understand as to why it came up with this decision. And for exactly the same group, the model explanations leak more information. So there is this inherent trade-off there for this kind of methods for model explanation. We move quickly to looking at the privacy risks of algorithms that are designed to protect the models against adversarial examples, and a particular class of algorithms which are known as adversarial training, where instead of training the model by minimizing the loss on in exact points in the training set, we are going to minimize the loss on the vicinity of the neighborhood of the training data. So instead of training on single points, we're training the model, we're minimizing the loss on a ball around training points, and hopefully making it harder for adversarial perturbations of the data to cross the decision boundary and lead to wrong predictions. So this, as you can see visually here, would change the decision boundaries of the model around the points in the training set, because here again, we are empirically minimizing this loss, the loss on the ball around the training data. And to an adversary who looks at the predictions from the data points that were in the training set versus predictions of data that were in the test set, non-members of the training set, it would be very clearly able to detect by just looking at the loss value and the neighborhood of the query points to see if the data point has been part of the training set or not. So the loss distribution for the training data versus the loss distribution for the test data changes significantly compared to the on robust models compared to the models that are trained using standard stochastic gradient descent. This is a very strong signal for the attacker to run membership inference attacks. And as we can show here, when you have a standard training where the model is not robust at all, the inference accuracy is around 50%, which is a random guess of a data point being member or non-member. But as we make the model more robust using adversarial training, we also increase its susceptibility to inference attacks. What is very important is that adversarial training requires a larger capacity, a model with a larger capacity, in order to be able to fit all the balls around the training data and find the decision boundaries around them without much overlap. And this results in increasing the vulnerability of the model with respect to inference attacks. So by decreasing the capacity of the model, we perhaps improve its privacy, but also we sacrifice robustness or the potential to making the model robust, and also the predictive power of the model. So here we have this relation between accuracy, robustness, and privacy. Moving to fairness, here the question is, again, if I want to make the model fair with respect to groups identified based on some sensitive attributes, for example, gender or race, whether that might result in reducing the privacy of individuals in those groups. So we focus on group fairness, and in particular, methods that are designed based on equal opportunity or equalized odds that try to equalize the prediction error of the model across different subgroups. So for this, we look at how much is the privacy risk of the model for different individual and different subgroups using group-aware membership inference attacks. And we also quantify the memorization of the model with respect to different data points in different subgroups, where the memorization is measured as how much is the influence of the data point on the loss of the model when we add or remove that data point to the training set. So with this, we can identify actually what are the most vulnerable points or subgroups in a fair model compared to an unconstrained model. So here, when we look at this distribution across different data points in different subgroups, we identify that the smaller subgroup of the minority group is the one that has maximum privacy risk and is the one that is memorized the most in the fair model compared to the unconstrained model. So if you are a member of the minority group and on the class for which it is the smaller size, then the information leakage is going to be more significant. It is not very hard to explain this because now with the added constraint of group fairness, where we want to equalize the error of the model across two groups, the influence of this smaller group is significantly increased in a disproportionate way compared to the majority group in order to be able to get more or less the same error, right? So the influence of individual data records in the minority group is much more than the influence of the individual data points in the majority group. And that is what leads to more information leakage about them. So when you look at the smaller subgroup of the minority group, which is the most vulnerable group, we'll see that they do gain some accuracy due to the fairness constraint, due to the fairness guarantee. So their accuracy, the prediction accuracy increases compared to the unconstrained model where they had low prediction accuracy. But at the same time, their privacy cost increases. So that accuracy gain comes with a privacy cost. And this is a dilemma here because the fairness issue with respect to prediction accuracy is more or less solved, but this causes another fairness issue, which is with respect to privacy. Now, the minority group, again, suffers from something. There is a disparity, and the disparity is on privacy, on the data privacy that they have. So here we are back to the first square, where we were asking, okay, whether we can actually implement different trustworthy ML algorithms and satisfy different properties. When we look at the nature of the trade-offs that we try to evaluate through the lens of data privacy, we see that some of the trade-offs are there due to the definitions. For example, when we talk about group fairness, equalizing the error across the two groups, this definition would lead to increased privacy risk. And some of them are due to the methods, for example, for interpretable machine learning. When you are, or model explanation, when you're using the gradients or local approximation for explaining the model, you are increasing the privacy risk with respect to the training data, but maybe that's not the only way to do model explanation, and other techniques might be more consistent, let's say, to data privacy definitions. Or, for example, for adversarial training used for robustness is one algorithm, is one class of algorithms, and other classes of algorithms which may be designed in the future or have been evaluated in the past might not be as vulnerable to privacy attacks. And the last bullet here is that usually the trade-offs between, say, property X and privacy has another element. So we have a triangle there, and that is the model accuracy. So usually the trade-off is less significant when the model accuracy is low, right? So when the model accuracy is low, maybe privacy and fairness are not at odds with each other, but when you want to maximize accuracy, when you increase the capacity of the model, then you'll see that these trade-offs become more dire. So to wrap up, what is the way forward? There are many points, but I want to highlight a couple of them here. That the risk minimization in the optimization problems for machine learning should go beyond prediction error. So the question that we need to ask as a community that works on machine learning is whether it really matters if we can gain a little bit in prediction accuracy for a huge cost in the energy of training the model, using the model, and also the risk that it might have on privacy and fairness and on individuals. So we need to, instead of having a single objective or an unconstrained optimization problem, we need to bring multiple objectives or multiple constraints into that optimization problem so that we solve this problem by considering all different types of risk, whether for robustness or privacy or fairness, along with the prediction error. Without that, there is no way that this problem could be solved. So we need to move towards those multiple objective optimization problems. And when it comes to evaluating different definitions or different methods, they need to be actually evaluated and analyzed in a holistic manner, where we don't look at one dimension of it, whether the robustness increased or the accuracy increased, but rather we look at the side effects that it might have and the consequences that it might have for other criteria under trustworthy ML. So I'd like to wrap up here, and I'll be very happy to follow up. If you have questions, please send me an email, and I'll be happy to follow up and discuss these. Hopefully, we'll see each other in person for the upcoming events, and we can all work on this very interesting set of problems towards trustworthy ML.